As you can see here, I'm continuing from the last video's example where we were using implicit differentiation in order to find the second derivative, and I had made an error in cleaning it up, and so I wanted to correct that. So I will continue to clean it up, and we will hopefully get to the correct answer. On the left side of my equation, there's nothing to clean up. We just have our notation for the second derivative, which is exactly what we want to find. On the right-hand side, we can actually just reorganize some things. Negative 2 times y can be written as negative 2y. And then you'll notice we have dx over dx, and that's just a fancy 1. So we don't really need to continue to write that notation. It cancels. Minus and minus becomes a plus, so we have plus 2x times dy dx, dy over dx. So that does not cancel, that needs to stay, and the entire thing is going to be divided by y squared. Alright, so because we're finding the second derivative, we need to do something a little bit more advanced in this type of problem than we would if we were just finding the first derivative. And what we actually need to do is we need to get rid of this. We need to get rid of that dy dx, and in order to do that, we're going to resubstitute, or actually re is probably a bad use of that We're going to substitute dy dx into this expression, and earlier we had found a dy dx negative 2x over y. So this is what we'd found in the first step of the problem, or the first several steps where we found the first derivative, and what we need to do is we need to substitute that back in. So d squared y over dx squared equals negative 2y plus 2x multiplied by the first derivative, negative 2x over y. And we still have the entire thing divided by y squared. And at this point, it's all about algebraic manipulation to get all your variables combined here, all your like terms combined. So if I continue on over here, what I can do is I can multiply these two fractions together. So negative 2y will just drop down, and then we'll have minus 4x squared over y, all divided by y squared. What's going to happen now is subtraction in order to combine these terms. And the subtraction requires a common denominator. So I'm going to get a common denominator, I'm going to subtract those two, and then ultimately I'm going to divide by this y squared. So it's all about just cleaning it up and getting all like things together. So common denominator wise, this you can think of as over 1, which means that y will be your common denominator. I need to take that first term and multiply by y on the top and on the bottom. And my second term already has a denominator of y, so there's no need to do anything different there. Now at this point, because all three of these terms do have y's in them, you could do a little bit of reducing, but I'm going to hold off and do it at the end. Let's see what we have now. Alright, now that I have a common denominator, I'm going to go ahead and write both numerators over that one common denominator. So I've got the negative 2y squared minus the 4x squared all over y, 1y here, and then divided by y squared. Let's do the division. So I'm going to take my numerator, which is that fraction, and I'm going to multiply it by 1 over the denominator. Copy dot flip, if you're familiar with that term in terms of dividing fractions. What I have from here is that the denominators multiply to be y cubed. Whoops, that's a y. and the numerator multiplied by 1 just stays the same. So my final answer for my second derivative of this implicit differentiation problem is negative 2y squared minus 4x squared over y cubed. And that is in fact correct. So we've now finished everything we need to in terms of lecture for this week.